Good afternoon, everyone as well. Welcome to the online webinar talk on the flood risk management and the early warning system organized by the Environmental Engineering Technical Division, the Institution of Engineers Malaysia. So I'm Engineer Chu. I'm the moderator for today's. So here we have also the speaker, Mr. Niksa Orlic. Okay, the talk will be 2 hours from 2:30 to 4:30. Okay, and let me brief a bit of the synopsis for the talk today. So, Mr. Nixon, my voice is okay for you so far?
Yes.
Actually, working on the topic related to the flood risk. So, you know, the global flood risk is increasing due to the factors such as the climate change and the population growth, and making the flood a major threat to the communities and the infrastructure worldwide. So flood also caused significant damage to the properties, disrupt the transportation and the communication networks, and result in the loss of life and economic productivities. So to combat the disaster risk reduction of the various disaster, including floods, the World Meteorological Organization has launched the early warnings for all the initiative. So this technical talk has covered the various aspects of the flood risk management, including the flood risk assessment based on the continuous hydrological monitoring, selection of the suitable hydrological instrument for the continuous monitorings, proper monitoring site selection, equipment installation, and maintenance. So, and implementation of the early warning system and real-life data. So perhaps Mr. Niksa will brief more during the talks. So basically a brief introduction to the speaker today. We are happy to have the Mr. Niksa Orlic, who is the co-founders of the Geolux, a Croatia-based companies that specialize in the development of the hydrological instrumentation with the emphasis on the contactless water levels and discharge monitoring. He holds the master degree in engineering and has 16 years of the experience in the environmental monitoring industries. So during the past 5 years, Mr. Ori has been involved in you may start your talk now. Thank you.
Okay, so can you hear me well now?
Yes, you may start
okay.
now.
Thank you very much. Thank you very much for
we have about 100 plus participants. Yes.
Thank you for the introduction, both to the topic that I will be discussing and to the as well to information about myself. My name is Niksa Orlic, and as you have mentioned, I come from Croatia, where currently I am managing a company which I also co-founded, which is Geolux. And Geolux is a manufacturer of instrumentation and software for environmental monitoring. Through the work at this company and some previous work, I have many times encountered the problem with floods. Currently, we manufacture instruments which are used in here, and I would definitely like to share some experience and some information about early warning systems that are implemented for flood, for protection from flood events. And also, in more general terms, I would like to share my experience about the different flood risk management projects in which I was involved over the past 10 or more years. So to start with, flooding is, as you know, one of the natural disasters that can hit us. Among other types of natural disasters, such as earthquakes or fires, floods actually generate the highest damage annually. So compared to all other events that are natural disasters, floods are generating the biggest damage in terms of the life loss and in terms of damaged property. So while earthquakes can suddenly create a huge damage at one location, so then often in the news we can see some disastrous news about an earthquake here and there, and then many people die in one event. But the floods, they affect really almost the whole globe or many countries. And even though they are maybe somewhat smaller events, each flood, but when they add up together, they really contribute to the most damage and to highest loss of life in the world. And for this reason, the World Meteorological Organization is promoting early warnings for all initiative, because early warning systems are one way, one technological way, how flooding can be, how negative effects from flooding can be mitigated. Of course, there is much more to flood risk management than just the early warning systems. And this is what we are going to discuss today. So to start with, I will share one video which was taken in our country in Croatia during a recent flooding that we actually had just 2 weeks ago. So even though this talk was announced much before that, in our country we have experienced some flooding very recently. And this is taken at one monitoring site. I will play the video. I hope that you will be able to see the animation. Every picture is taken every 1 hour, so you can see over the few days how the water level is first stable, and then the water level starts to increase, and then within less than 1 day the water level suddenly goes up and floods the complete area. So this video was taken from images at the site, taken over the period of 1 week, but you could see that for the 6 days the water level was constant, and then suddenly in 1 day just the whole area was flooded. This is one small string, so you can of course imagine, and you have seen this in your country as well, that floods come suddenly, and they can of course cause great damage. So in terms of flood risk management, I will just replay this video once again if it did not go through. So again, you can see how the water level just suddenly starts to rise, and then again it floods the whole area. In terms of flood risk management, we can talk about 3 things. The first one is detection. Detection is something that we actually do when the flood has already started. So without any earlier preparing, detection is an immediate action that can be done during the flood to mitigate or to minimize the damage caused by floods. Then if we try to look a little bit more into the future, this is prediction or forecasting. So we can forecast the weather, we can forecast the rainfall, we can have some river models or flow models for rivers, so we can forecast the water level, and we can warn people in advance that the flood is coming. We can warn emergency services to prepare for a potential flooding. We can tell people to maybe avoid some unnecessary travel during the season when we can expect heavy flooding, and we can tell them which areas will be flooded. So we can maybe evacuate people in areas where we can expect really heavy flooding. So prediction is something we can do to mitigate the flood risk maybe a week in advance to the flood or a few days in advance. And finally, the third thing is planning. Planning is something that we can do even many years in advance to mitigate or to minimize the flood risk. Planning, I will talk a little bit more about it later. Planning involves things like construction works, public education, but do the planning properly, you need to have a lot of data to do it in an efficient way. So for example, if you want to build a dam, you need to know where to build it. You need to know what height it needs to be and so on. So just once again, flood risk management we can split into three items. The first one is detection, and this is something that is done during the flood. So to detect it as early as possible and just to send out warning maybe a couple of hours before flash flood hits an area. Prediction is something we do maybe up to 1 week in advance. So we prepare for a flood, we have time to move or to evacuate people and to warn people, and we have time to plan for the emergency operations. And finally, planning is something we do years in advance. The first part is the detection. So to detect water level, which is changing due to the flood, you need to have a network of sensors that are installed on various rivers in an area where you want to be able to detect the floods. There are many kinds of instruments that are used to measure the water level. Here you can see one of the instruments which are produced by my company. This is a radar-based instrument. Radar-based instruments are installed above the water surface. So the benefit of using this kind of technology is very easy installation and low maintenance due to the fact that the sensor is not exposed to the water. Other systems are pressure transducers like a bubbler system or a hydrostatic probe, which are typically, not typically, but which need to be installed at the bottom of the river channel. And then by measuring the pressure of the water column above the sensor, these instruments are able to measure the depth or the water level. And of course, the older systems use floats or buoys and then a counterweight and that some sort of rotary encoder which moves as the water moves up and down, so it is possible to determine the actual water level by the system. But it is not only enough to monitor the water level. You need to transmit this data in real time if you want to be able to warn the people of an incoming flood. The system which monitors water level or even water discharge at a site without the telemetry or with the telemetry that is not real time is not able to give early warnings to people. This kind of network, of monitoring network, can be used to gather long-term hydrological data that is useful for the third type of the risk, flood risk management. So that would be planning. But to do early warning, to detect incoming flood, you need to have real-time telemetry. Also, a little bit later, I will discuss different types of telemetry and how to do it properly, because I have seen in many projects done over the past 10 years that sometimes telemetry systems were existing, but they were not adequately planned. So the data was not actually coming in real time, even though initially the telemetry system was planned to be real time. The implementation of this system was not adequate. And finally, to do the detection properly, you need to have a monitoring station network, which, how to say, it has the monitoring sites in the right positions. So you can have a dense network of various tributaries, river tributaries, or a confluence area And it is not enough sometimes to measure at 1 or 2 positions the water level or the water discharge. It needs to be measured on all the major tributaries which can contribute water to a downstream area where the flood can be expected. This is a part where hydrologists are very important. So their understanding of the river basin area and the water flow in that area is critical. So the monitoring station network you can see in the next slide. This is the part, this is 1/2 actually of the hydrological network in Croatia, in our country. You can also see some of the rivers that are indicated, and generally in Croatia we do not have one or several, actually we do not have multiple major rivers. We have only one major river and then many smaller tributaries which all contribute into the main river. So in Croatia it is crucial to have many water level and discharge monitoring sites on all these smaller tributaries, because depending on the weather conditions and on the rainfall or on the melting of the snow, sometimes the flood can start from one region of the country, sometimes from the other region of the country. And sometimes you can have very heavy rainfall in a small area that creates the flood, but sometimes you can have steady rainfall, which is not of high intensity, but which is really affecting the whole country. And then all these small tributaries have slightly increased water levels, but when this river discharges into the biggest river, then suddenly you can have flooding downstreams. And in fact, this is what has happened in our country almost 10 years ago. There was a heavy flooding in an area which is somewhere. So this main river flows from the west to the east this way. So there have been some. There has been a long duration of the rainfall for maybe 2 weeks, which was not high intensity, but it covered the whole region. And then downstream, all of this water actually accumulated, and the area downstream was heavily flooded, with big damage to the property and also with loss of life. So to mitigate these kind of effects in the future, in Croatia, the government agency is modernizing the network, which consists, or it will consist in the end of more than 600 different sites for measurement of water level and water discharge. And we as a company are supplier and are involved in this project, so we also learned a lot about these bigger projects in terms of the hydrological monitoring and real-time data transmission. The next step in flood risk management is the prediction. So unlike detection of the flood when it already started, it is much better if we are able to predict that the flood will happen. And not only predict that the flood will happen and when, but also what area will be affected. Typically in every country there are emergency services that can do things like building of temporary embankments, doing some evacuation of people at an area that will be affected. But these emergency services, they are typically limited in number of people or manpower, and in a terms of number of vehicles that they use, and so on. And also to build some temporary embankments, it takes time and so on. So it is very good if in a flood risk management system, or if a government agency that does flood risk management, if they are able to do prediction and predict where and when the flood is going to happen. Of course, there are many things to do this prediction. One is meteorological data or weather forecast, where the rain will fall. If the floods are generated not by rainfall, but by a snow melt, which we see in Europe, then also the melting of the snow layer must be analyzed and used in these prediction models and so on. But from a barely hydrological point of view, to be able to do prediction, you need to know your river network, basically. So you need to have bathymetry measurements to know what is the capacity of each channel. You need to do continuous monitoring of the water level and water flow on multiple sites to be able to do, in the end, modeling and forecasting of the flow, because all of this data that you collect over many years will enable you to develop an accurate model of the river network, and will be able to do forecast in an accurate way. So with this prediction, from hydrological point of view, there needs to be a lot of work done many years in advance, actually, so that the models are accurate. And here again, we come back to measurement of water level and of the water flow, for which again you need to have a dense network of monitoring stations placed around the country. Another thing which is critical for the prediction is the dissemination of forecasting data to the public and to emergency services. So there needs to be a system in place that the forecasting data, that the flood warning data few days or a week in advance is disseminated to the public and to the emergency services. I have seen several examples in several countries where we have implemented this kind of projects, or where our equipment was used, where very important, it was during the planning of the project, the high importance was also given to this data dissemination. So there are protocols in place which say that depending on the forest for the forecast for the flooding, there is a way how the data is sent to the public, that they are warned. In some countries, this is going to be on the news or with the weather forecast. In some countries, they have smartphone applications that send the warning to the public and so on. For the floods that hit my country recently, 2 weeks ago, we were having warnings approximately 1 week in advance. And we as a public were informed where flooding can be expected. People were advised to cancel all unnecessary travel to the area that is going to be affected by floods. And local authorities were notified of that as well. So the roads were also being closed by local authorities at an area where road flooding can be expected. And finally, the planning for the flood risk management. This is something that we can do many years in advance. And planning can give us actually the biggest protection, and it can reduce the damage caused by floods more than prediction and even more than detection. So just to recap, detection is, we know flood is coming in 1 hour or maybe in half an hour. You can just maybe, in some cases, you can leave the area that is going to be affected by the flood. You can perhaps remove some very expensive things that are stored in warehouses which can be damaged by the flooding, but there is not a lot that can be done. If you know a few weeks in advance, then you can evacuate more people. Warehouses can move more of the things or the goods that are stored there, which can be damaged and so on. But still, infrastructure can suffer big damage. With planning, you can even protect the structure and the whole parts of the cities and so on. And planning is, the good example is that here in Malaysia, you have the smart tunnel. This is a good example of the planning of the flood risk management. So this is a heavy investment into infrastructure that is able to mitigate damage coming from the floods. So these are, for example, construction works like dams, tunnels, embankments, reservoirs, discharge channels, and so on. And in many countries, I see this construction work as a primary way to do the planning in ahead and to reduce the damages caused by floods. However, what we see more and more over the past few years is the education, the importance of education, the education to emergency responders. So how to act when the flood, during the flood event, how to properly do the evacuation or other responses. So in some countries, unfortunately, there are emergency responders, but they typically during the flood event are assembled on an ad hoc basis, and there they did not receive sufficient training, just some very general training, or they received the training in terms of the first aid, but not the training related to the flooding. And it is important to train emergency responders how to safely operate during the flood event. So it is important, like for example, for fire, this is done for firemen. They know when they enter the building on fire, how to do it safely for themselves. Unfortunately, in many countries, what we have seen that emergency responders are not generally trained how to behave in a proper way during the flood, or at least just some small part. But because the floods affect so large area, there are actually many emergency responders, typically also military personnel is involved, and the military personnel did not, in some cases, receive sufficient training of how to act when they respond to the flood event. So it is very important to do the education of any kind of emergency responder personnel that might be involved. It is also very important to educate the general public. So this is the general education in advance, especially in the areas where floods can happen more often. This is typically done, for example, the general public is trained in areas that are affected by earthquakes, how to behave during an earthquake. In countries that experience some forest fires which can affect the cities as well, there is a fire drill or fire training. In areas that are affected by tsunamis, general public is educated how to behave in an event of incoming tsunami, or even to recognize the signs by themselves that tsunami can be incoming. So the same thing should be done in areas that can be hit by flooding. General public should be educated how to behave in an event of the flood. And the forecasting information, so this is actually something between the previous step, so the prediction step and the planning step, is to have the protocols for informing the public that the flood is coming. So you need to plan in advance these protocols, how to actually share the data with all the relevant parties, so that when you do forecast, you already have these protocols in place. So I would say that from a planning perspective, the most costly, of course, is the construction, but of course, the construction itself makes the biggest saving from the damage of the floods. Education is not very expensive, and it also has a big effect, especially in to change the way how people behave and to save the life at flooding event, while construction work is targeted to saving both life and property. Education is more targeting to saving life. And finally, people should be informed about incoming flood in a timely manner. Now, I have mentioned that for all these three parts, so for the detection, prediction, and planning, it is important to have accurate and real-time data about the water level and the discharge of the water in rivers and channels. So for the detection, you need to have the data in real time to be able to warn the public. For prediction, you need to have the data collected over many years so that your forecasting models are accurate. And for planning, you need also to have the long-term hydrological data for the water levels and for the floods, so that you know where to build the dams, how big the smart tunnel needs to be in the end, and so on. Coming from a company which is manufacturing this kind of instruments, I can share some of the technologies that are used over the past few years to deliver accurate and precise data. So to get the accurate measurement of the water level and discharge, you need to be aware that this kind of instrumentation is installed out on the field. So these instruments, first of all, they need to be reliable. They need to be able to operate under all kinds of atmospheric conditions. They need to be able to operate under high temperatures or low temperatures, depending in which climate zone they are installed. They need to be able to operate when the weather is hot, when it's humid, or when it's dry, because you do not want to have this data only during rainfall, but also during the dry season, so that you can do the prediction and forecasting accurately. The sensors should provide accurate reading, especially when there is a heavy rainfall. And to do all of that, the instruments need to be able to be installed and maintained easily, because to have more accurate data, you will have more dense network of the monitoring stations, like on this map. And this is not the full map, this is just the half of it. And then again, if you need to install a lot of sensors, you will want these sensors to be able to be installed quickly. If you have a network with many monitoring sites, you will want low maintenance, because low maintenance means that you will not need to have many people employed to do maintenance. It will not be expensive for you. And finally, low maintenance means that the sensors themselves are robust and that you do not expect any failures to happen. And especially you do not expect failures to happen during a flooding event, when this data is very critical. We have seen over many countries where we work on this kind of projects. In some countries, they just measure the water level. So they have many monitoring sites where water level is measured. And to get the discharge of water, so the flow in cubic meters per second, they do many calibrations where they use an instrument such as an ADCP or a hydrometric wing, for example, like a propeller, to measure the velocities across the whole channel and then to calculate to get the discharge of the river. Not many, but more and more countries over the last few years, they also started to perform continuous discharge monitoring. So not to measure only the water level, but also water discharge. And there are many different kinds of instruments that can be deployed on the field to perform discharge monitoring. There are contact instruments such as an side-looking Doppler instrument. This is an ultrasonic instrument which is submerged into the water and uses the ultrasound principle to measure the velocity of the water flow. There are also non-contact instruments such as the radar-based sensors, which measure the velocity of the river flow from above the water surface. And I would like to discuss this method a little bit more because it provides many benefits, such as the ease of installation and low maintenance, which I have just mentioned before. So as an illustration, I will use the instrument which is manufactured by our company. You can see the picture of this instrument, and this instrument actually consists of two different sensors, two different radar sensors. The one you can see on the bottom part of the instrument, and this is the blue circular one. The blue circular instrument is a radar-based water level sensor. It measures how long it takes for the radar waves to travel from the instrument to the water surface and then bounce back to the instrument. And the longer it takes, of course, the water is further away from the instrument, and then using the simple calculation, the instrument can determine the water level. The other instrument, which is in front of it and tilted at 45 degrees, is also a radar instrument, but this is a different kind of the radar. This radar uses Doppler effect to measure the velocity of the water as it flows beneath the sensor in the river. And the combined instrument uses these two separate radar sensors, which operate together to get the surface velocity measurement and to get water level measurement. And then this instrument combines these two measurements to derive the total discharge of the water in the river in cubic meters per second or any other unit which is desired. Now, the question is, how is this instrument able to determine the complete discharge of the river if it measures just the water level and the surface velocity? And this is something that I am going to discuss now. However, just before we go into discussion of the discharge calculation method, I would just like to outline once again the benefits of using non-contact technology. The first one is fast and easy installation. So this means that you can, if you look at the picture on this slide, this is one monitoring station, radar monitoring station installed above a river in somewhere in Europe. I'm not sure exactly where. And the installation of this station, which was pre-assembled on site, it was required less than half an hour to install it. So this is really, really fast installation, and there is no need for any technical personnel to enter the water to install the equipment into the water. So it can be done even during light rain or even heavy rain, but this is maybe unnecessarily dangerous in those cases. But you do not need to wait for low water conditions. You do not need any special tools or cranes or things like that. So in this case, if you install it on the equipment, if it is installed on an existing bridge, then the installation is really, really quick. The maintenance for this is very low. So when our customers ask us what kind of regular maintenance is required, we say we recommend that you visit the site once per year and that you do the visual inspection of the equipment on site. So there is no regular maintenance required for the instrumentation. There is no regular cleaning required for these instruments. There is no regular recalibration required. So there is no need to disassemble the equipment and send it to laboratory or to the service department to do the recalibration and then to put it back. So this means that you will have continuous measurements without any interruptions. And this also means that the cost of the operational costs are low. What, in terms of maintenance, what kind of problems do we really see with this kind of equipment? Well, the main thing is that for the radar instruments to work, the area between the sensor and the water surface must be clean of any other object, so that the radar beam, which is transmitted by the radar, can freely propagate to the water surface and be reflected back. So sometimes if the channel is very narrow where the measurement is being made, it can happen that some vegetation grows or that a tree branch grows in front of the radar, so that in that case it has to be cut down to provide the clear operation. But since this vegetation does grow slowly, really it is not required that the visual inspection is done very often. On some sites, but this is maybe one of several sites out of few thousand that we have installed, we would see, for example, hornets building their nest all around the instrument, and then this hornet nest was blocking the operation of the radar. Or somewhere the cables were damaged by small animals like a mouse or squirrel. They would simply bite the cable so they could be damaged. Of course, this is something that can happen to any other equipment which is installed on the field. But on the other hand, it is very important to note that the hydrological equipment, which is outside of the water, requires much less maintenance than the equipment which is installed inside the water, because there is no sediment flowing around your instrument, no mud. There is no floating debris like a tree log or a tree trunk which can be carried by the water during the flood that could hit your equipment. So And of course, there is no accumulation of limestone or calcium on the instrument that would need to be cleaned. So in terms of maintenance, of course, some maintenance and visual inspection is required. Of course, there is a possibility that there are some problems simply because the equipment is exposed out on the field. But compared to the instruments which are inside the water, non-contact instruments have really much bigger durability and much lower maintenance. And finally, what is also possible is to have ad hoc measurements, which means that you can go on site at one point, temporarily install the instruments, make some measurements for an hour or for a few days, and very easily and cheaply remove these instruments. So fast and easy installation also means that ad hoc measurements or short-term measurements are possible. And now for the engineers, we go to a very interesting part of my presentation, and this is how do we calculate discharge of the river by measuring the water level and the velocity of the river flow at the surface. So to start with, I would just like to point out that discharge measurement, so to measure how much cubic meters per second of water are flowing to the channel, we do not use any direct method. So I always give as an example the direct measurement of discharge. So the only way how to directly measure discharge would be if you have a river that flows toward, let's say, like a big swimming pool, a rectangular swimming pool. It's empty. There is a floodgate at the entrance. We open the floodgate and let the river flow into the swimming pool and fill it up, and we start the stopwatch. Then we wait for some time as the water fills up the swimming pool flowing from the river. Then we close the floodgate or we redirect the water flow elsewhere, and we stop the stopwatch. We check how much water there is in this pool, so we know the volume. We check the time on our stopwatch, we know the time, we divide, and then we get the total discharge of this river. So this is the only direct way how to measure discharge, to actually measure the volume and to measure the time and to divide it. Of course, it is highly unpractical. So all the methods that actually we use today are some indirect methods. For example, we can use a partial flume and then measure how the water level distributes within the flume because of the hydrological properties of the water flowing through the flume. So this is indirect measurement. You know the size of the flume, you measure the water level at the flume, and then you extrapolate using hydraulical formulas or empirical measurements done earlier, you get the discharge. This is an indirect method. Or for example, the other example, you can measure the velocities on several points across the channel profile, and let's say at 2 or 3 different depths. And then based on these velocity measurements, you calculate the average velocity and then use this as an input for discharge measurement. Again, this is indirect measurement because you do not measure discharge, you measure only velocities, you measure the area underwater. And again, there is some extrapolation done because you measured velocities only in, you measured the velocity only in several points and you extrapolated the distribution of velocities between these multiple points. And also to calculate the area, you had to estimate the actual area because the channel profile measurement is never 100% accurate. So the discharge formula in general, in this case, for the flow in the river, we can say that, or not we can say, but it is, the discharge is equal to the cross section of the area underwater, so this is the blue area, multiplied by the average flow velocity in the cross section. So this area could be in square meters. If the velocity is expressed in meters per second, then we can easily see that the discharge is expressed in cubic meters per second. How to calculate? So to calculate discharge, we need to know the cross section of the area underwater, and we also need to know the average flow velocity in the cross section. How to calculate these two values? By using a radar-based flow meter. The first step would be to calculate the cross-section area. This is easy if you have a radar-based water level sensor to determine the actual amount, the actual height of the water in the channel. But you also need to have bathymetric measurement of a profile of the river channel. So at some point, you will need to do measurements of the cross-section of the profile channel. And then if these measurements are done in the points which I have indicated here with the white lines, you can divide each of these, you can divide the big channel into so many smaller channels. And then based on the water level and known depths for each sub-channel, you can simply calculate the total area underwater as the sum of the areas for each of these small channels. So to calculate the area underwater, you need to measure the water level, which is easily done by a radar-based water level sensor, but you also need to know the cross-section profile for the river. An important point here to note is that the profile of the channel can change over time. So for example, if there is an accumulation of sediment at the riverbed may become more shallow over time. If the strong water flow erodes some part of the area or the dirt or whatever material is below the channel, then it will become deeper over time. So it is very important that hydrologists who use this equipment, that they are aware how much their riverbed changes over time. So if there is a river where the change of the cross section at the measurement point is big, or it happens very often, then the bathymetric measurements should be done more often to have an accurate discharge measurement. However, if the riverbed is maybe made from stones which really don't move over time, it is sufficient to make one bathymetry measurement maybe every couple of years. So again, to have the best possible results for the discharge calculation, it is important to understand the conditions and what is happening actually with this river, so that the bathymetry measurements can be planned and can be done as often as required. So basically, they should be done whenever the profile of the cross section changes. The next step is how can we determine the average flow velocity across the profile if the radar measures only the flow velocity at the surface. On this slide, you can see some approximate distribution of velocities across this channel profile. So typically for rivers, the fastest flow is achieved at above the deepest part of the channel, which is for many rivers somewhere in the middle of the channel, and slightly below the surface, perhaps at 90 or 80 or 95% of the depth. It, of course, depends on the roughness of the riverbank and on the depth and on the slope of the channel. These velocities then get slower and slower as you move closer towards the ground. And of course, at the ground, because of the slowdown due to the friction of the flow, the velocity drops suddenly to zero. To be able to get the average flow velocity across the channel based on the surface velocity measurements, we will introduce something that we call K factor. This K factor is a very fancy name for nothing else but a simple ratio between the velocity measured at the surface by a radar instrument and the average velocity across the whole channel. These K factors, they need to be determined. So for every monitoring site, the K factor is different. However, the good thing or the beneficial thing is that the K factor does not change a lot when the water level changes up and down. So for a channel like this one, which I took for the slide presentation, it would be sufficient to determine a K factor by doing on-site calibration for the water level, which is illustrated right now. And then if the water level goes up for 1 meter, or if the water level goes down to 50% of the water in the picture, and if you would do another calibration, then you would see that the K factor has changed only a few percent. So what we recommend to our customers when they operate our equipment on such site is to actually perform 2 or 3 calibrations of the K factor, and not more than that is required. So one calibration should be performed when the water is at its annual average level. The one should be performed when the water level is very high during the flood event, and the final one should be done when the water level is very low during the dry season and when the water is very shallow. So some of you who are familiar with Manning equation that is used to estimate the discharge in channels, you know that in Manning equation there is something called wetted perimeter and wetted area or area underwater, and that the amount of discharge as calculated by Manning equation is affected by the relationship between the area underwater, this would be the blue part in this image, and the wetted perimeter. This is the length of the line which is underwater. So when the water becomes very shallow, this ratio becomes very big. So the area is still pretty big, becomes lower. The area of the underwater is low, but the line is still very long. And then the flow conditions change. So for this reason, because the flow is affected by the actual ratio between the area and the perimeter underwater, then we say that the K factor should be again calibrated for the shallow waters. On the other hand, when the water level is very high, so when it's higher than the average value, we again suggest that another K factor should be calibrated under such flooding flow conditions, because during flooding, again, the distribution of the velocities and this ratio between the surface velocity and the average velocity will change. In many cases, you have a lot of vegetation that grows on the river banks. And when the water floods, this vegetation introduces a bigger slowdown to the water flow than what is expected under normal regular flow conditions. So again, to have an accurate measurement or the accurate calculation of the discharge by using K factor and the surface velocity measurement, K factor should be determined on an average water level that is expected during the year, during the minimum flow, and during the high flow or the flooding event. And just as I have explained, so the K factor will not change greatly for small changes for different water levels, but only when the water becomes very shallow during the flooding. And now the question is, how can you calibrate the K factor? What does this calibration involve? For small rivers, typically flow meters hydrological wings are used, or like a small propeller or electromagnetic sensor. So a person would walk across the channel. They would measure maybe every 1 meter apart or every few meters apart, flow velocity would be measured. And also on several different depths, velocity would be measured. By making these multiple flow velocity measurements across the channel profile, you can easily determine the average flow velocity. And then you take the average flow velocity that you have determined by making manual measurements across the whole channel, and you take also the radar measurement of the surface velocity, you divide these two values, and you get the K factor, just like in this formula. On bigger and wider rivers, it is impractical to do the calibration with the flow meters. So on very wide rivers, it would take a long time to cross the river. Perhaps even the flow is so fast that it is not easy to put the flow instrument deep inside the river. And in those cases, an ADCP instrument can be used. Typically, the ADCP instrument which is attached to a bottom of a small boat. So this small boat can be pulled either from, excuse me, either from a bridge which is above the water, or it can be also taken or towed by a boat. If the ADCP instrument is being towed by a boat during the calibration, it is it is important that the boat motor itself does not influence any turbulences that could affect the ADCP measurement. So if there is a bridge on site which is not too high above the water surface, it is recommended to use the ADCP which is pulled or towed from above the bridge. ADCP has unfortunately also some downsides, and one is that there is some blind area directly below ADCP where the ADCP cannot make accurate measurements. So the ADCP is lacking the measurements of velocity at the river surface. And then there is also a problem that just next to the bottom of the river channel, again, ADCP is not able to make accurate measurement. So it has like a small dead zone or small blind zone at the bottom of the channel and at the top of the, or close to the surface. For these reasons, if the water is very deep, then the blind area for ADCP will be very small, and the error introduced this way will be, it can be simply ignored. However, if the water is shallow, even for wide rivers, it's better to use the flow meters and to do manual calibration than to use ADCP, because simply they are introduced by ADCP for very shallow waters. So I would say less than half a meter. This kind of error would be too big. And finally, the K factor for artificial channels, like the channels made from concrete. For these kind of channels, it is not necessary to do the calibration, because the K factor can be determined by a hydrological modeling. So for example, the software that we deliver with our sensors, using this software, it can be easy to define the type of the channel and the width of the channel, or to define the whole channel geometry. And if the channel is made from concrete, you can use the K factor estimation, and it will be as accurate as on-site calibration. Estimation can also be used for natural rivers, but if you estimate the K factor in natural rivers instead of using ADCP or flow meters to do the real calibration, you can expect some loss of accuracy between 10 to 20%, depending on the also accuracy of bathymetric measurements. The benefits of using surface velocity methods, there are several of these benefits. The first one, this is continuous discharge measurement. So if you want to measure discharge at a certain point of a river, you can always go there with an ADCP, for example, the ADCP boat. You can pull it across the river and you can get measurement of the discharge. However, this is not, that is not continuous measurement. You had to go to site, you had to perform the measurement from an ADCP. Sometimes you need to do some small post-processing or cleaning up of the data, and then you will get the discharge measurement at one point in time. And it is expensive to do it again. So you do it just for the calibration typically. The radar-based method for the discharge measurement is continuous discharge measurement. So it will provide continuous real-time information about the discharge on a certain site. You can have this sent by telemetry data to your system. You can have many hundreds or thousands of monitoring sites across the country, and all this data will continuously be fed into your system to allow you to do real-time prognosis or warnings or alerts and so on. In many countries, we have seen that still they use rating curve method to measure the discharge. So by using rating curve method, this is also continuous measurement. In this case, only water level is measured continuously at a monitoring site. And then ADCP calibrations are done much more often to determine discharge for various water level conditions. So perhaps every month, hydrologists or the technicians would visit the site with an ADCP or with a hydrometric wing, do the measurement, they would note the water level, and they would enter it in a table. And finally, with this measurement of the rating curve, you would get something like this. So on the vertical axis here, they plot the water level. On the horizontal axis, they plot corresponding discharge. And then, because there is a big change on, so for each water level, they would get many different discharge readings. They need to take some average value, and this is the red line which is displayed here. So you have continuous measurement of water level, and then just based on the water level, you go on this graph, check the position of the red line, and take this discharge as the current discharge measurement. However, this rating curve method has at least two main downsides. And the first one is that if we compare the surface velocity method to the rating curve method, we can see that the surface velocity method is not influenced negatively by the hysteresis effect. So what we call the hysteresis effect. This is just what I have explained. For a single water level, so maybe for this reading here of, let's say, 150 centimeters of the water depth, you can see very wide spread of the different discharges for the same water level. So why is discharge different for the same water level? It is caused by many facts. One is, for example, different slowdown coefficient of the water throughout different periods of the year. You may have more dense vegetation at one part of the year, so that when the water flows through this vegetation, it is introducing more slowdown. And then during the other time of the year, there is less vegetation, so the water is not so much slowed down, and there is a bigger discharge for the same water level. The other reason for different discharges at the same water level is hydrological or flow properties of the water. For example, if there is an upcoming flood, what is happening is that there is really a large mass of water body upstream of the river. And this enormous mass of water body, because of the gravity, is pushing all this water downstream to flow. And now you have the water level, which is rising maybe from half a meter, and it's rising up because flood wave is incoming. It reaches 1 meter, and at that point we can say that flow is maybe 200 cubic meters per second, and it continues to rise up. At some point, the flooding passes, and the water starts to recede and move down. And now going from 2 meters of water level, or 2 meters of water depth, it goes down, 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 reaches again the same 1 meter. However, because there is no more this big mass of water upstream that is pushing the water, now the discharge will not be anymore 200 cubic meters per second, it will be maybe 150. Now, if you just make the measurement of the water level and use the rating curve to determine the discharge, you'll use this red line. And both times when the water level was rising and when the water level was receding, your system will estimate that the discharge was some average value, maybe 175 cubic meters per second. But this means that your initial estimate during the incoming flood was too low. So you estimated lower discharge than the actual discharge that can cause potential flood. And this is a problem, especially if you want to provide early warning downstream to the people and if you want to do accurate forecasting. The surface velocity measurement fixes this problem. So the surface velocity will change also with the discharge. If the discharge is bigger, the surface velocity will be bigger as well, and you will measure this bigger surface velocity and you will output the correct discharge. On the other hand, when the water is slowing down and again and falling down and reaches the same meter, the surface velocity will be also lower. So again, you will report lower discharge, and that is more accurate than estimating discharge purely from water level measurement, and from the rating curve. You can also see some other graphs that explain hydraulical properties of the flow and how the flow rate is changing when the water is rising or when it's falling. So we call this hysteresis effect, and there are also some other names, but also if you want to Google it for more information, another term is looped rating curve or dynamic rating curve, or you can also search for terms such as kinematic wave. The other benefit of using the surface velocity method can be seen on rivers that have reversing flow. Typically, there are two kinds of rivers where the flow direction can be reversed. The first one are tidal rivers. So the rivers with confluence into the sea, which are affected by the tide effect of the sea. So every time when there is a rising tide, the flow direction of the water can be reversed and some part of the water can flow inland. With the surface velocity radar, it is possible to determine the flow of direction. And if there is a farming area close to the sea, which is negatively influenced by too much salt water, you can easily use the surface velocity radar to know when the fresh water is flowing outside to the sea. But you will also be aware when the seawater is coming inland. So to prevent the crops, to prevent the farmland, there are many cases where you can then close the floodgates and so on. Simply by measuring the water level, you will never know if the water level is rising because the river flow has increased or because the high tide is coming. Or you would need to have many mareographic instruments to measure the tide and to compare this against the water level measurement and so on. So it is much simpler just to have the surface velocity measurement in place. The other situation where reversal of the flow can be expected is the confluence of two rivers. And if there is high and sudden increase of water level in a bigger river, it can push the extra water into the smaller tributary. So in case there is a monitoring site in a smaller tributary, which is close to the confluence point, then you will measure and you will detect the increase in water level in a smaller tributary. If there is a surface velocity measurement as well, then the surface velocity sensor will be able to detect the reversal of the flow direction. And then you, as somebody who is analyzing the data, will know that the smaller tributary is taking extra water from the larger river, and not that both the larger river and the smaller tributary have both increased flow. So just recapping again, I have seen in many projects that measurement of the discharge and continuous measurement of discharge is very important to do proper alarming, proper forecasting, and proper planning to mitigate the flood risk. There are many benefits of using non-contact technology for discharge measurement, such as low maintenance, fast and easy installation, and the robustness and the resiliency of the instruments when they are operating under tough environmental conditions. And finally, by measuring the surface velocity and the water level, an accurate discharge, so the discharge can be calculated in a very accurate way. Of course, in order to get the accurate measurement, and this is what is required, so to plan for the flood protection, to be able to mitigate the risk from floods, to be able to give accurate forecasting, it is critically important to have accurate information about the flow and the discharge and the water level. And I can also show you what we do on our side as a manufacturer of these instruments to provide the highest accuracy. So I will show one small video how we calibrate and test our instruments when developed. I hope that this video will go through the presentation. So this is a huge tow tank. The tow tank is like a very long swimming pool. This one is 380 meters long, so 380 meters long. it has a big platform on it, and this platform can be moved in a controlled way with a controlled velocity above the water. So we place our sensors. So sorry, this one is 270, not 280 meters long. The sensors, the surface velocity radars, are placed above the water on a platform. The platform is moved in a controlled way with an exactly accurate velocity, and then the measurements from the sensor can be calibrated. So using this method, we ensure that the instruments to measure surface velocity, which are produced by Geolux, they can operate within this tested range from 2 meters per second to 12 meters per second with the accuracy of less than 1%. And in a smaller tow tank, which is based in Switzerland, so for this other tank, I do not have a video, we calibrated the sensors from 0 to 2 meters per second. So for the full range of the operation of the sensors, I will just show the video once again. For the full operational range, the instruments have been tested in a controlled way in the tow tanks. So for the smaller velocity in Switzerland, and for larger velocities in a big tow tank in Croatia. I'll just let the video play to the end, and then we will move to the next slide. So to make the conditions as realistic as possible, we also have this steel rod inserted into the water to create some disturbance on the water surface to create the waves, as this is what can be expected with the river flow. And this is the equipment on the platform which makes it move and control the way. So the title of this presentation is Flood Risk Management and Early Warning Systems. So far, I was talking mostly about flood risk management. So what can be done to manage the flood risk, and how to collect the data, which is essential for the flood risk management. And I have also highlighted one of the modern methods which are used to get the discharge data that is required for the flood risk management. The second part of the presentation is how to implement early warning systems. So early warning systems, they have basically two goals that need to be satisfied. The first one is real-time flow detection, and the second one is reliable alarming. So with the early warning system, you need to be able to know when the flood is happening, and you need to be able to raise an alarm and to send this alarm to people. I will give you an example of the such system setup from Malawi, a country in Africa. And here you can see a graphical representation or a schematic diagram that illustrates the case for one early warning system. So there is a river, there are some higher areas from which the river flows, and then you can see number one, this is the water level monitoring station. So the first part is there needs to be a site where the water level is monitored and that sudden increase in water level where it can be detected. So for this Malawi case, we have a distributed, not centralized system. So there is no centralized forecasting that would distribute the alarms to the towns and to the villages, but instead, few villages have their own monitoring site, which is making measurements continuously, and then the alarms can be sent from the site. So you can see, first of all, there is a site which monitors the water level, and then when it detects the sudden increase in the water level, and if this increase is above a certain threshold, then a radio link, the purple one, is used to send the alarm to the villages. Each village has a tower with a siren and some alarm lights, and then these sirens go on and sound an alarm to people so that people can move away from an incoming flood. So in some, these are typically some lowland villages and so on. Unfortunately, in Malawi, the buildings are very weak. They're not strong houses, but they have maybe one or two stronger buildings. So in case of alarm, people will either climb on the floor of these strong buildings or move further away from the river. So to allow the water to spread from the river, but they will be outside of the range of the flood. So each of these villages or towns have a tower with a radio receiver equipment, with a siren, and it can receive the measurement, and it can, whenever the water level monitoring station determines that there is an increase of the water level, an alarm is sounded. This is distributed via a radio link. The secondary data distribution channel is the GPRS link, or 2G, 3G, 4G, and so on, which sends also the measurement data from the water level monitoring station to some data collection center or data storage server, which is deployed somewhere, either in the cloud or in some data center and so on. And the data which is sent to this data storage server can then be distributed to mobile phones to send additional alerts to people via mobile phones, so using some sort of messaging. So from this water level monitoring station, the alarms are sent using two different link types to do different kinds of users. The first one uses radio link to distribute the alarms to people in village who need to really quickly move away from the incoming flood wave. And then the second data link distributes the information messages and alarms to people via their mobile phones. The alarming part of the system consists of these sirens, and in some cases also alarm lights. And of course, the other part of the alarming is the messages which are being sent to the mobile phone. As I said in this previous slide, so one is real-time flow detection, but also reliable alarming is critical. And there are several considerations about the data transfer that need to be satisfied or to be considered in order to provide reliable alarming. And we have seen this in several of the projects where we participated. So you need to be aware that GPRS network, while it is very versatile and typically widely available, it can be unreliable. The first reason is very simple. So perhaps some area is not covered by the GPRS signal. And perhaps one village downstream is an area where some houses are not really covered by the GPRS signal. If you rely only on GPRS to send an alarm, it is possible that it will not reach everybody. But a bigger problem with the GPRS is that it is a public network. This is not an isolated network, and it is used by all people within an area. During a flood event, and we have seen this in many countries, as well as in our Croatia, when a flooding happens in an area, people start calling emergency services. People start calling police or a fire department or whoever is in charge of the evacuation. People start calling their family members to ask if they are well, to ask if they need help, or to ask for help. And what happens is that the GSM GPRS network, and the same network uses all these 2G, 3G, 4G, whatever, it's congested. And if you have flood monitoring data site or the water level monitoring station that uses only GPRS connection to deliver the data, it is very possible that the data link will be unavailable during flooding event because of all the people who use the same network and who use the same infrastructure to place so many phone calls. I have personally experienced a very similar situation 2 years ago during a different kind of natural disaster. there has been a strong earthquake in my country. My city, we just felt a very strong earthquake, but there was no damage. However, some 30 or 40 kilometers apart, it was highly damaging, with more than 10 people dying due to the earthquake. And immediately after the earthquake, because it was so strongly felt in my city as well, I was working in the office, and I wanted to call my children who were at home, just to talk to them, to console them, and so on. And I wasn't able to place a phone call for more than 45 minutes because of so many people who were also doing the same thing like I did, calling relatives, calling family, and so on. And in the flooding, during the high flood, the same thing happens. And then you cannot transmit any data. And in fact, during this earthquake, which struck our country, later we went to analyze the data from the monitoring sites which we operate in our country. And we saw that all sites which are close to big cities, they were not able to transmit for a period between 15 and 45 minutes until the congestion were down. Of course, the equipment, for example, the one which we produce, if the data is not able to be transmitted in real time over the GPRS link, then the RTU will store the data temporarily and just retransmit it later. So in the long run, you don't lose the data, but still you do not have real-time information about increasing water level. You could use some other data communication, maybe satellite, but the satellite problem is that some satellite operators can have high latency. So you can measure the data, you can send it, but it will be received on the downstream station maybe 15 minutes later or half an hour later. And from our experience, we have observed that in order to send real-time data with no loss of latency and in a reliable way is to install a direct radio link between the water level monitoring station and the alarm stations, such as those that have sirens or alarm lights and so on. So taking all this into account, we can go back to the schematic diagram, and you can see that the radio link, the purple one, is being used to send the warning or alarming data to the sirens, so that the people in this town or villages can be alerted immediately and in a reliable way. But also to provide wider distribution of warnings, we use the GPRS link, which most of the cases is available. However, the alarms that are being sent to the mobile phone sometimes can come a little bit late or can be delayed. But the important part is that all the areas that can be flooded have local sirens or local alarm lights which use reliable direct radio link communication to the water level monitoring station. And finally, it is also important that the equipment health of all these sites is continuously monitored. So if they're operated by a solar panel, then the battery status and the solar panel health should be transmitted periodically to the central data storage system. So if there is any problem with equipment, that it can be detected early by maintenance personnel, and that they have enough time to go on site and to resolve the problem, maybe to replace the battery, to clean the solar panel if it is dirty. In some African countries, we see accumulation of sand material or dirt material on the solar panel, which prevent it from operating properly and so on. But if your equipment is able to monitor all this and transmit it to the centralized solution, which is accessible by maintenance personnel all the time, then also maintenance is easy, and you will be sure that when you need this equipment to work, that it really will work, and warn people about an incoming flood. And now moving forward to the end of my presentation before the Q&A part, I would just like to share several pictures of various kinds of installations of the monitoring equipment, which are used either for early warning systems or for planning of the various flood risk mitigation projects. So on the first picture, this one I believe is taken very close to Malaysia. This one is from Thailand. This is a system with flap gates on the side and this channel and so on. And the white part that you can see at the bottom of the picture, this is an instrument which is the flow sensor, radar-based flow sensor produced by our company. So then this sensor can actually monitor and verify that the amount of discharge taken into this channel under certain conditions is as it is planned. Then for change some pictures from Europe, from Croatia, where we are from. Here you can see how we install these instruments from a riverbank or from the embankment when the channels are narrow. So this arm, this cantilever, contains the radar level sensor and the surface velocity Doppler radar sensor on the top to measure the flow velocity and to calculate the discharge in this kind of channel. And this is one of the channels that actually, this is what part of the network of channels which all flow into this big river that I explained you before. So it is important to measure discharge at this point to know exactly what can be expected downstream. On the right part, there is also a floodgate, and these sensors are used also to send information to the personnel who are then deciding when to open the floodgates to optimize the flow of water and to manage how the water will be distributed across the various channels. The sensors have also been used in various mountain rivers, like the picture on the left, which is from South America, or the picture on the right. This is one of the installations on the bridge with an additional cage just to protect from the vandalism. But you can see easily that if there is bridge present on site, it is easy to place the equipment on site and it's very easy to access it. And when maintenance is needed, if it is needed, it's very easy to reach the sensors. On the left image, the arm, the cantilever, is approximately 5 meters long. It can also be longer, like in this picture. So if it is required that the cantilever is longer, that it's maybe that it extends more to the water surface. In this picture, you can see that it is this one is approximately 10 to 11 meters long. But to prevent the vibration of the instruments, there are many tension wires, support wires that keep the cantilever arm safe from any vibrations. When installing radar-based instruments above the water surface, it is important to prevent any kind of vibrations. The vibrations itself will not disrupt the water level measurement so much, because the water level sensor makes multiple measurements and then calculates the average value. So it will just average out all these vibrations. However, the surface velocity instrument or the surface velocity sensor, it is affected by the vibrations. So for this reason, when a longer cantilever arm is used, then it is important to make it stay in place. On this picture, you can also see some other installation on top of the bridge, where it's very easy to install because the bridge structure is in place. And again, the site is small, it's compact, easy to install, and continuous measurements are provided. And finally, just to complete with my presentation before the Q&A, this is a screenshot of a system that receives such data. But if we have just a few more minutes, I would just briefly like to show you what this system looks in live. So I can connect to the live data system in our country and just show you some pictures from that. So please give me 1 moment to change my screen to the other system. So I'll just stop sharing briefly this one and then share again the live system, and you will be able to see live data from a complex system that provides early detection of floods. So just a moment. So I will now share a different screen, sorry. So just wait a brief moment. So just a few more seconds. So here you can see what initial login screen looks like. So there is a list of many sites that receive the data, receive water level and discharge, and some sites even receive water temperature data. Since this is from an ongoing project, so far approximately 130 sites have been installed. Some of the sites are currently undergoing installation, so for them you would see red indicators that the data is not being sent to the system. On the right side with these indicators, you can see the health status of the data being transmitted. If this is green, it means that all the data for a certain day was sent. And there are seven squares, each one indicating health for one day in the past week. The ones which are red do not transmit anything. The ones which are yellow, they do transmit some data, but not all, due to very weak GPRS signal on site. And now we can go and click on a certain site to actually see measurements. So this site, which I have now just randomly selected, it has a camera on site as well, which gives us snapshots maybe every hour or every 2 hours. So we can slightly scroll back and we can see what the flow conditions were at a certain point of time. I will also zoom in the picture just so to see what this river, it is a small river, but this one can also flood a lot. And you can see here the current measurements of the water level and diagnostic information like a tilt angle of the sensors to make sure that they have not been bent, that they are looking perpendicular to the water surface, and some battery status and the strength of the signal and so on. And then also historical data can be explored. So here you can easily see the flow, the water level graph on this site. So you can see that on the 17th May, there was some increase of the water level over 1 meter. So we can even try to get a picture for that by going back and trying to find the picture from the 17th of May. So perhaps this picture you can easily see. So if we go and we select the picture from the date when we saw that the water level has been increased, then we can see that the water level is high if you compare it to some of the pictures I have just shown you before, or from the latest picture, in fact, which was taken right now. This site which I have now selected, it does not measure the discharge, just the velocity, but if there was a discharge measurement instrument, there will be another graph with the measured discharge. And then there is the ability here to configure various alarms, to configure also important feature is that it is very much it is possible that the scanning interval, the measurement interval is maybe every 15 minutes to make the measurement of the level and discharge. But if the water level passes certain threshold, then to automatically change it to 5 minutes or to even 2 minutes, so that during the flood we get more accurate data with a higher resolution. So just let's pick some other site, some on the random, maybe some of these lower ones, so we can also see what are the conditions for some of these other sites, or maybe a third one also, just like an example. So you can see that in this system, it is very easy to integrate a really big number of the sites that send the data, and the system automatically measures all of this information. The system is able to raise an alarm, to send SMS messages from an alarm, to send some other messages to the smartphone, and so on. And again, here are the latest measurements, and then we can also see some flow graphs and so on. So different conditions, etc. So so far, with this we have completed the presentation, and I would be very happy to answer any questions that you might have.
All right. Thank you, Mr. Niksa Orlic. Can you hear me?
Yes, I can hear you.
Yes. Thanks for your very interesting sharings. Just want to check, is there any question raised by the participants? For those who like to ask question, you may want to write your question on the question sections. Okay, so perhaps I have a few questions. Okay, the first question, how many years of input do you need for the historical data?
So this is very difficult to say, because ideally it would be more than several years, but it is not always possible to get so much data. So what we typically say to people who want to do forecasting or planning is that start collecting data now, or as soon as possible if you are not already collecting it. And then after perhaps 1 or 2 years, the initial planning can already be started, and there will be some data for forecasting. And then just over time improve your models. So as more data is being collected, do not use the same model which you have derived after 2 years, but improve it. Improve it after 3 years with the 3 year of data. After 5 years, take the 5 years of data, improve your forecast model again, and so on. So you have to start somewhere. Of course, in some sites, you may have data for the last 50 years, which is fantastic. But if you do not,
Wow,
you should start getting it. And the minimum is to have 1 year of coverage because of the seasonal changes throughout the year.
Yeah, the 1 year will be the good basis because of the seasonal change. But in Malaysia, we don't have the 4 seasons, but perhaps it's still good to have a 1 year's data. Anyway, okay,
Yeah.
thanks for your response. So, okay, other question is more on do you provide certificates? Yes, I think we will have e-certificates for the audience, okay, for the participant. Okay, the next technical questions, how does the predictions for floods related to the rainfall forecast, how do you accurately predict the floods 1 week
So
in advance? Yeah, where the rainfall forecast could be highly variable and unstable.
So about the forecasting, so the forecasting itself is not my area of expertise, but I can share some general information that I'm familiar with. So for the forecasting, hydrologists, they build models. There are some softwares that help them build this kind of models, where they basically need to map out the river sections within an area, and then there is a way how to correlate the rainfall data for a certain area, which is typically measured by rain gauges, and the corresponding water level for these areas. So basically there are some software which hydrologists normally use to do the forecasting. So I am not an expert on this topic, so I do not know exactly how this is made and so on, but I do know what kind of data accuracy needs to be provided for this software. So the continuous measurement over at least 1 year, to have a dense network of the river stations and so on. So this is important, because otherwise these softwares that are used for prediction or for modeling, they will not have simple enough data, they will not be able to give good results.
All right, so there'll be another specialist or expert that perhaps we can work to with them for another webinars. Will be very helpful for our engineers and members here. Okay, so thanks for your quick sharing. So I think the other question also related to the forecasting. Okay, for the flood forecasting, do you also need to monitor the rainfalls? So what
Yes.
software do you use the flood forecasting?
So again, there are many of kinds of this software, but I'm not so much familiar. But yes, the rainfall is one important input into that.
Okay, thanks. Perhaps if any more question, perhaps you can email to Mr. Niksa to perhaps can provide some relevant information. Is that okay, Mr. Niksa?
Okay.
Yeah. So the next question is, how can we improve in terms of times to notify and alarm the people of incoming flood for more than 2 hours? For example, 6 hours in advance, or what are the expected durations?
So this depends. So how to improve the alarming time? It depends again on the geological conditions for various countries or various regions. So in some regions, simply the it depends on the river network mostly. If you have one large river which is long and the tributaries are small, then you can have an upstream station which is tens and tens kilometers away, and then this flood wave passes. It will take maybe even 6, 7, 8, 9 hours to come to some villages downstream. So in that case, it is very simple because the water is it takes some time for the water, for the flood wave to propagate. In other cases, you can have an area like in a valley, and then you have many small rivers which flow towards the valley from a different sites or different sides, mountains which surround the valley. And in these cases, typically the flooding can come much faster, because after the rainfall,
Fast.
the groundwater starts going out at the springs for many small streams, and then it just flows down where it accumulates and creates the flood. So this depends very much on the terrain configuration, also on the geology, and depending on that, you can have either warnings really several hours ahead or even a day ahead, or you might have just an hour, 2 hours to give the warning of an incoming flood. So for this reason, I think that the second step, which I said, and that is forecasting, it is very important, because in a second case, like a valley surrounded by mountains where the flooding can start fairly quickly, if you were able to forecast a huge amount of rainfall in the area and warn the people to maybe leave the area in advance or just to take care and so on, you will be able to do really much better preparation for the flood event. And of course, the idea, if you want more time for the warning, you need to go further away from the site, more upstream. In some cases, this is of course possible, sometimes not. So this is, unfortunately, here you are very much dependent on the characteristics of the surrounding terrain.
Yeah, I think that would be quite sensible to look into the geographical profile, okay, from the areas, topography as well. Okay, thank you. How widely have this system being used within the Malaysia? I mean, your monitoring system, perhaps. How
So
widely used is it?
in Malaysia, we haven't implemented the system as such, but there are many monitoring stations to provide the water flow or water discharge and water level monitoring data through our partner in Malaysia, the Surechem company. Otherwise, elsewhere we have, so our products are used in over 60 countries in the world, somewhere in very small systems, or to provide this data that is later required by modeling, so to provide continuous data. And the early warning systems we have also implemented in several countries, the largest one being our country of Croatia, the system which I showed you in live. And the most recent one that we are doing right now is the one in Malawi. And also the one which is very recent is one in Uzbekistan. So in the Fergana Valley, this is the eastern part of the Uzbekistan. So this area is the valley between the mountains, like I just explained.
All right. Thanks for your information. I think, yeah, there are always a lot of opportunities to work with your teams, okay, in Malaysia. Another question could be, what is your solutions to overcome signal latency or signal loss issue on the data transmission? Is there any solution? Because I believe, yeah.
So there is there are, let's say, two levels of solution. The first level is to make sure that if there is a signal loss which is temporary, to be able to deliver the data at a later time. So the data is stored internally at a remote site, and it is made sure that it's transmitted whenever the signal becomes available, so that not only the recent data is transmitted, but also old data that is not in the main system yet. However, this will not give you a warning. So if you need to provide a warning, then the best way is to have two different types of communication. To use maybe GPRS and the secondary radio link, like in Malawi. The picture which I showed, there is a radio link for alarms, which is a reliable one, and there is a GPRS for the general data exchange. On the other hand, in the project in Croatia, they use GPRS again as a primary data link, but they do not use direct radio LAN, they use LoRaWAN radio network. This is a not direct point-to-point radio, but the benefit of LoRaWAN is that it is independent of the general public. So when general public starts to make a lot of phone calls, as I said, the LoRaWAN network will remain not congested, and the data will be able to be sent there. So to give reliable data transmission, I think the best way is to have two different data links. So if the primary link fails, then the secondary link can take over.
Okay, thank you very much for your response. Perhaps one last question. I know we have short of time, so perhaps we can take one or two more. Now we have about 130 participants now, just for information, Mr. Niksa, 130. Okay, so it's a very good response. So okay, so any experience of a fault alarm, what could have caused it for alarm, 40 alarm perhaps? Do you have any
Sorry,
experience on
what?
that? The false alarm,
The estimate of the cost.
the 40 alarm, I mean the any problem with your alarm, perhaps alarm system, alarming
For the
system?
alarm system. It's
Yeah,
very much depends on the, so so you ask about the cost for the alarm system.
yeah, the cost, yes.
Okay, so this unfortunately very much depends on the amount of the construction work that is required. So it can be, so I showed the pictures, for example, to install the instruments. If there is an existing bridge where the equipment can be installed, then this is not really very expensive. But if you need to do the cantilever construction, the concrete base, and so on, then it can very quickly get costly, unfortunately. So, for example, for this project in Malawi, since it is in Africa and they are not in an economically favorable situation, then the World Bank is actually financing a big part, or maybe the majority of this project. So on the other hand, of course, it is much less than some construction which is required to build the dams and so on. So it's difficult to give me some answer because at some point the cost of the construction work can easily be bigger than the cost of the equipment itself, which is on site, and it very much really depends on the where you install it, the configuration of terrain, is there a bridge present or not, what is the distance. So these radio links for shorter distances, they are less expensive than the long distance one. There are really many factors that contribute to the cost.
Okay. So thanks for your response. So if you have more clarification, perhaps you may look for Mr. Niksa. Okay, I think the slide, actually the handout has been uploaded on the webinar. You may download for those who are interested to know more information or detail from the Mr. Niksa Orlic. So yeah, I think perhaps thanks for your sharing today. We almost going to end to our sections. So how frequent you will come to these regions? Perhaps are you going to have more frequent trip to Malaysia?
Yeah, so definitely, because we do plan some more projects in Malaysia and also in the region in the future. So we definitely do, not only myself but also my colleagues. We do plan to be more frequent in Malaysia and also Thailand and so on, some other countries in the region.
Yeah, hope that one day we can see you.
Yeah,
physically,
we are aware of the
face to face.
high flood risk, for example, here in Malaysia, and this is why you have this fantastic smart tunnel which was built just to mitigate it. So this is a fantastic example of the construction works that are used to mitigate the floods, and a good example to other countries. So for us, this is also very good, how to say, use case. And unfortunately, some countries are not in an economical, they do not have economical strength to build such a project, but then at least they can do some, at least early warning to reduce the number of casualties. But thank you very much for giving me the opportunity to talk about this to such a wide audience. Thank you very much for your time. And I also hope to be able to see you or meet you again somewhere in the future.
All right, I think thanks again, Mr. Nixon. Thanks for all the participants. If you'd like to welcome again, you participate our events for the next webinar, if any. If not, the physical IEM talks. Okay, that's all for today's. Thank you very much, Mr. Nixon. See you.
Thank you.
Bye.
Okay, see you. Bye.